Good morning everyone. Welcome back to the class. As in our last class we have seen the expression for the mathematical expression for kinetic energy, which is K is equals to half mv square. Here we are with our new topic of the chapter, which is work-energy theorem. Now if you see the name of the topic, work-energy theorem, we already have seen that how work is related to energy, how the work is a form of energy. So this is what the relation in the statement we are going to see, that work energy theorem. What is the statement of the theorem? How are we going to describe that work is a form of energy, or when the energy changes, how the work is done? And also we are going to see the derivation of this thing. So sometimes in sometimes a question asks the state and prove work energy theorem. State means you need to write the statement, and prove what what derivation we are going to see. So let's start. Here we have the statement work energy theorem. I have already given you the idea, like we are going to see how work is related to the change with the change in energy. Now let's read it. The work done by a force. Let's take a body of mass m. Okay, now let's say that the body of mass m is moving already with the velocity, initial velocity u. Okay, so the mass of the body is m and the velocity of the body is u. Now if I ask you what is the velocity, what is the kinetic energy of the body, as we have learned the expression for kinetic energy is half mv square. So kinetic energy here, if I write half m, what is m? That is of course m given, and v square, v simply denotes or tells you about the velocity. So here what is the velocity? U. So that is u square, isn't it? Half m v square or half m u square. Now this I have written. Now this is the initial condition of the body, or initial velocity of the body. So the energy possessed, the kinetic energy, because the body is in motion, which type of energy it will possess? Of course kinetic energy. So the kinetic energy, can I write it as initial kinetic energy, since this is the initial condition? Now what will happen if we apply a force F on a body? Like if I tell you there's a body moving with a velocity and it will have some kinetic energy. Now if we apply force on a body, of course the body will accelerate. Like accelerate means the velocity will change or velocity will increase. So let's say when we are applying the force, the same body of mass m, now when we are applying the force, like if a ball is moving, okay, that is the initial condition, and when you kick the ball, that means you are applying a force. So of course there will be increase in velocity. So now the velocity is becoming v. Okay, so now if I ask you what is the kinetic energy in this condition, so kinetic energy will be half, since mass is going to be same, m, and now v square. This is our situation initially, and this is our let us take this is a final situation. So if I write it as f, so kinetic energy initial half m u square, because the velocity was u. Final kinetic energy will be half m v square, as the final velocity is v. So it is, if I write it clearly, this is just the notation kf. Kf is equals to half m v square. Now this is initial, now this is final. Now if I ask you, of course we know that v is greater than u, final velocity, since the body is accelerating. Let's say the uniform acceleration is a, as we are applying a constant force f. So body is accelerating. We have learned in the previous class that if a body is accelerating, that means the initial velocity is less than the final. That means the velocity is increasing. From 30 meter per second, the velocity is going to be 60 meter per second. That means velocity is more. The body is accelerating. So the final velocity is greater than the initial velocity. Now if I ask you, in which case the kinetic energy or the final kinetic energy, which one is more? Of course, since the final velocity is more, so kinetic energy final will be more than the kinetic energy initial. So if I ask you what is the difference or what is the change in kinetic energy, if I rub this, okay, now what is the change in kinetic energy? So change in kinetic energy will be kf minus ki, that is final minus initial, that is the change in kinetic energy. If I write it like this, change, we have learned that this is the symbol delta is for change. So change in kinetic energy final minus kinetic energy initial. Now what is the expression for final kinetic energy? Half m v square minus initial, it is half m u square, isn't it? And now what we have learned, the work done by a force on a moving body in the same direction, like body is moving, we are applying the work done and it is in the same direction, is equal to increase in its kinetic energy. Now this is the change, this is the increase in kinetic energy, and this must be equal to the work done. Now you can see the expression. If we see, the change in the kinetic energy will be equal to the work done. Now this is the statement of the theorem, Work-Energy Theorem. This is the statement and this is the mathematical expression. Now we are going to derive. This is the statement we are going to derive. Okay, let's see the proof of this Work-Energy Theorem. Let's take a body of mass m, okay, with initial velocity u. Now we are applying a force F on a body, and let's, for an example, you can take a ball, you can imagine a football moving, and like the mass of the football is m, it is moving with a velocity u. Now when you are applying a force, there will be change in the velocity, and let's say the velocity is changing to v. This is the initial velocity of the body, this is the final velocity of the body, and when you are applying force, the body is having an acceleration, a constant acceleration a, okay. So from u to v, the body is changing its velocity, having acceleration a, and the displacement it is having is, let's say, it is s, okay. So this is the condition. Now we are going to see, okay, we have to, what was the statement, that we have to calculate the work done and it should be equal to the change in kinetic energy or increase in kinetic energy. That means basically we have to calculate the work done. How do we calculate the work done? What is the expression? That is force into displacement. What displacement we are taking? S. And since it is in the direction of force, so it is okay that we are not writing cos, that cos 0 will be simply it is. So W is equals to force into displacement, okay. Now force, if we talk about, force is simply mass into acceleration, we already have seen. So it will be mass. What is the mass of the body? That is m. Acceleration, it is having a into s. This is our work done supposed to be. Now what is the idea? We are going to calculate this as displacement of the body, or how much displacement there will be in the body, and we are going to put the value. You keep this in this expression in the mind. We are going to put the value of displacement here, okay. So now let's see. To calculate the displacement, we are going to use the one of the equations of motion, the third one actually. Third one is v square is equals to u square plus 2as. If you see, this is exactly the same step we are following as we did to calculate the that kinetic energy, expression for kinetic energy. Okay, now the only difference is here the final velocity is v and the initial velocity is u. Now the final velocity, since it is already v, so we will write it as v only. Initial velocity in our condition also we have taken u, so it will be u square. 2a as it is, acceleration we have taken here. Now you need to keep this in your mind that here we have to calculate this s. How to calculate s? We will take rest of the things to the other side. So of course it will be v square. Now this u square is with plus sign here, it will come here and it will be minus u square. Right side we are left with 2as. We have to calculate s, which means this 2a, which is in multiplication with s, will come to the other side, and since it is in multiplication, it will come here in division. So simply it is v square minus u square. It will come here in division upon 2a, and it will be equals to s. Now since we have calculated the value of s in terms of this v, u and a, we are going to put this value of displacement in our expression of work done. Now see, I'm gonna write, I'm just simply, okay. Now what was the expression we have written? We have written work done is equals to force into displacement. Our force was mass into acceleration into displacement. Now we are going to put the value ma into s. The expression for s we have calculated as v square minus u square upon 2a. Is it? Like the value of s, we are keeping the value of s. Now if you see this a and this a, we can cancel them. We are left with m upon 2 and v square minus u square. Okay. Now I am going to open the bracket. Now if you see m upon 2 into v square, that is m upon 2 v square, I can write it like this: half m v square minus m upon 2 u square, that is m upon 2 u square, and on the left side we have work done. Now if you see half mv square, v was the final velocity of the body, so this half mv square will be the final kinetic energy. If I denote it with kf, minus u was the initial velocity of the body, and half m u square would be the initial kinetic energy. Now if you see, we have reached to the expression where final energy minus initial energy, that means the change in energy, is equals to the work done. Is it clear? So this is what the mathematical expression of kinetic energy. Now one question for you is, you need to find out that why, if we are talking about in the work energy theorem, we are taking a statement that there is a change in energy and that would be equal to work done. We are only considering the change in kinetic energy. Why are we not considering change in potential energy? Because a body will possess both potential energy and kinetic energy. So why are we not, or in the expression, why are we not having any expression for potential energy? Can you think of it? Simple, that when the body, we are talking about the velocity change and everything, we are actually talking about a rectilinear motion in a horizontal direction. That means there is no motion under gravity. That means when the body is moving from this place to this place, there is no change in the height. And if there is no change in the height, position or configuration, we don't have any change in the potential energy. That means if a body is moving from one place to the other place, the rectilinear motion, there will be in a horizontal direction, there will be no change in potential energy. There will only only change in kinetic energy, and that's why we are having the expression for change in kinetic energy equals to the work done. So now this is what we are going to see. Our next topic is the conversion of energy. Like we know, the energies can be converted, one form of energy can be converted into other form of energy. We know there are many types of energies, as we have learned about the mechanical energy, kinetic energy and potential energy. The sum of kinetic energy and potential energy is mechanical energy, and it can be converted into the other forms of energy. We are aware of the other forms of energy like light energy, heat energy, numerous form of energies. We have tidal energy, we have chemical energy, we have nuclear energy, we have geothermal energy, we have solar energy. There are too many types of energies, and one form of energy can be converted into the other form using the proper method or using the proper system. Like if I take an example of iron means the press. If we are using that iron, we can convert the electrical energy into heat energy. We have an example of loudspeaker. It converts the electrical energy into sound energy. If we take microphones are the ones which convert the sound energy into electrical energy. And there are numerous examples you can see where we can convert one form of energy into the other form of energy, and that's what comes under the conversion of energy. Also, we are specifically learning here the mechanical energy. Mechanical energy means kinetic energy and potential energy. So we are going to see what happened to kinetic energy and potential energy. The sum of kinetic energy and potential energy is simply known as mechanical energy, and how one form of energy, that is kinetic energy, changes into potential energy. If I take a very simple example, like if I take a stone, it is at a height h, okay. A stone is at a height edge, like let us say this is our surface of earth and there is a stone at a height edge. Just now there is no motion in the body and it is at a height edge. So which energy it will have? Of course potential energy, and since it is not moving it will not have any amount of kinetic energy. But when we leave it, that means it is free falling under no external forces but gravity. That means when it is falling under gravitation, you see from this height where it is having potential energy, now it is falling. So when it is falling, the height is now reducing, the height is reducing. If h is reducing, the potential energy will be reducing, but at the same time it is attaining a velocity. That means it is gaining kinetic energy. So there we can say that kinetic energy is converting into potential energy. And this is what our next topic is, that what we are going to see, what is conservation of energy and how can we see that one form of energy is changing into other form and the whole energy is conserved. Conservation of energy, this we have learned in our previous classes, that what is conservation of energy. Like we have heard that energy cannot be destroyed nor created, it only can be converted from one form to the other form. Like we cannot destroy energy, we cannot create energy, but we can change the form of energy, like electrical to heat energy to into the different energy, electrical energy to light energy, sound energy to electrical energy, these type of conversion. So here what we are going to see is conservation of energy. That means energy is going to be conserved. We cannot destroy, we cannot create, but we can conserve energy. And specifically we are going to talk about mechanical energy. We know that sum of kinetic energy plus potential energy is known as the mechanical energy. And how are we going to say or going to see that the mechanical energy is conserved? Conserved means there is no wastage of energy, which means that kinetic energy and potential energy can change from one form to the other form. Like kinetic energy can change into potential energy can be changed into kinetic energy, but overall the energy is conserved. That means the sum is going to be constant. There is no, like if you are taking some energy, there will be no wastage of energy. One form of energy can be converted into the other, but the total energy is going to be conserved. That means the sum of kinetic energy plus potential energy is going to be constant. This is what our idea is. Okay, so we are going to see whether the sum, whenever there is a motion in the body and kinetic energy is changing into potential energy or potential energy is changing into kinetic energy, is the sum always constant? We are going to see this, and for that we are going to take a very common example in which we have both the energies. We are having the idea of both the energies, kinetic energy and potential energy. So we are going to see conservation of energy and we are going to see the proof that how can we, or theoretical, actually I should have said this, the theoretical analysis we are going to see. Theoretically we are going to see. For that I am actually going to take up an example of a freely falling body. We have learned what when we say that a body is freely falling. When we are having a body, this is your earth surface, and when we are having a body falling from a height, any height, under the force of gravitation only, there is no force acting on the body but gravitation, that then this scenario is known as the free fall. So let's say that we are having a body of mass m. This is the surface of earth, okay, and the body is at the height h. You can say, let's say that the height of the body is h from the surface of earth. Okay, I think this is clear. Now you all tell me, when the body is at the height h, and here is the body, what type of energy it will have? Is it moving? No. That means there is no kinetic energy. That means in this case, let's say that this is the position A. This is the point A where the body is, and initially when the body is there is no kinetic energy. That means K will be equals to 0. And now if the body is at height h, do we have any amount of potential energy? Yes, because we know that the potential energy is mgh. Mass is there, gravity is there, and there is a height. So the body will have a certain amount of potential energy that will be according to the expression mgh. What is the height? H. Is it clear? Now, So this is the scene. Now what we are going to leave the body, and the body is having a free fall. So when the body is coming down, it is coming towards the surface of earth. So let's say the body is coming, and here is, we are again considering a position, and this position, let's say this is the point B when the body is coming down. We are going to analyze the body at this point before coming to the surface of earth. Now at this point, if you see, from that point A, the body has covered a distance. Let's say the body has covered a distance x. Okay. Now I'm gonna ask you a question. You all tell me. Actually, what is our idea? We are going to take a point A here, then a point B while the body is coming down here, and then we are going to take a point C. And at all the 3 points we are going to see what is the position of energies. Okay. So now let us analyze the energy of the body at point B. Which energy is kinetic energy and potential energy. Now let's see at the point B. If I talk about kinetic, since the body is under motion, like body is moving, so body is coming down, so it will have kinetic energy. Yes, because the body was there and it is coming down. So when I stop it here, not exactly stopping, but I am analyzing it here. So of course the body is moving down, that means the body will have some kinetic energy. Okay. So what kinetic energy? We know that the expression of kinetic energy is half mv square. Half m. Now what is the velocity of the body? We don't know. Let's say that we are denoting the velocity of the body as vb. If I write it here, vb is the velocity of the body at point B. So according to our expression, k should be equal to half m vb square, isn't it? Half m vb square. Okay. And what about the potential energy? Potential energy will be m, as we know that the expression for potential energy is mgh. We have to take the mass of the body, the acceleration due to gravity, and the height. So now what is the mass is not going to change, it is same m. Acceleration due to gravity is g. Now what is the height? This is the distance covered by the body, but height is this, no, from the surface of earth. So this total is our h. This distance it has covered. So what is the remaining distance we have? H minus x, isn't it? Total was h. It has already covered a distance x. So what is the remaining one? H minus x. So what is the distance of the body at point B, or what is the height of the body at point B? Is this height? Now the height is h minus x. So mg, at the place of h, the height we are going to write is mg h minus x. So this is our potential energy and this is our kinetic energy. Okay. Now kinetic energy, just now we are unaware of the value of this vb square. So now our next is to calculate the vb square. And how are we going to calculate vb square? By considering the condition here at point B. Acha, by the way, before I write, let us write at point A what we have analyzed at point A. Okay. Now point A, we have to see the sum of kinetic energy plus potential energy. That was our idea. Now we have to see that the kinetic energy and potential energy, whether the sum is constant or not, whether the total is constant or not. So now let's see the total. Total energy, I am writing it as TE, that is total energy is kinetic energy plus potential energy. Now what is kinetic energy? Because the body is at rest, so kinetic energy was 0, as we have seen. Potential energy is mgh. So the total is mgh. This is at point A. Is it clear? So we have analyzed the body at point A. Now we are analyzing the body at point B. Is it clear, everyone? We are analyzing the body at point B. Now if we are going to analyze the body, again we have to calculate the total energy, that is kinetic plus potential, and we have to see what is the sum of the total energy. So kinetic energy we have written half m vb square, where we don't know the value of vb. So our next is to calculate the value of vb. So for that I am gonna write at point B. Now let's see. our idea is to calculate VB square. How are we going to calculate VB square? By using one of the equations of motion. So third equation of motion, that is V square is equals to U square plus 2AS. This we know. Now final, let's say the body is starting from A and it is coming to B. So what is the final energy or final velocity of the body attained by the body is VB. So instead of V, I am going to write VB. Initial, the body starting from A. What was the initial? When it is at height h, the body was at rest. Rest means the initial velocity was 0. So this U is 0. Now plus 2, the acceleration. Now it is a free fall. That means the motion is completely under gravity. So what are we going to write? We are going to write G. And what is the displacement covered? From here to here, what is the displacement of the body? X. So we are going to write X here. Is it clear? So now if I write it properly, VB square is 0 plus 2gx is simply 2gx. So this is the expression for VB square is equals to 2gx. Now this value of VB square we are going to put here to calculate the expression for kinetic energy. Half m VB square. So we are going to put the whole value here, that is 2gx. Is it clear? Now 2 and 2 cancel. What is the expression? mgx. So it is simply mgx. This is our kinetic energy mgx. And what is our potential energy? This is mgh minus x. Okay. So if you are done till here, our idea is to see what is the total value, kinetic energy plus potential energy. So I'm gonna leave this right line and I'm gonna rub this to see. Now at point B, the total energy we are calculating. Total energy is kinetic plus potential. We have calculated the expression for kinetic. It is coming mgx. Also we have written the potential energy, that is mgh minus x. Now this is mgx. I am going to open the bracket. This is mgh plus minus minus mgx. Okay, here I have opened the bracket. Now if you see mgx with plus sign, mgx with minus sign, so it will get cancelled and we are left with only one term, that is mgh. And this is total energy at point B. This was our total energy at point A. So now see, when the body was here at point A, the total energy is mgh. When the body is coming down, it is coming to the point B. Again the total energy is mgh. So from here it is mgh. Now it is coming here again mgh. Now let's see another point, so that what is the value of the total energy at point then. So I'm going to rub this so that I can write, of course. And now let's see another point. We have taken the energy at point A, we have taken the energy at point B. Now let's say the body is again coming down. Since it is moving, it is coming down, it is coming to a point C on the surface of Earth. Now when the body is hitting the surface of Earth, what will be the height of the body? 0. If the height of the body is 0, what will be the value of potential energy? 0, because mgh, h is coming 0. And now we are going to calculate the kinetic energy. Kinetic energy will be that is half m, and here let's say the velocity when the body is actually coming down and striking the surface. So it will have some velocity and it is actually striking the surface. So let's say when it is striking the surface, the velocity of the body is vc. So what will be the energy before the striking or before hitting the surface? What is the kinetic energy? Let's say half m vc square. Is it clear? And potential energy is of course 0, since the height is becoming 0. So potential energy will be 0. Kinetic energy will be half m vc square. Now our idea is to calculate this vc, the value of vc square. And here we are analyzing the energy at point C. So we are going to calculate this vc square. Again we are going to use the same equation of motion, that is v square is equals to u square plus 2a plus 2as. Now the body is starting from the point A. This is the initial point of the body, and now it has reached to a point C. So this is the final. So we are considering this as initial, this as final. So the final velocity of the body before it strikes the ground, we are taking it as Vc. So here final velocity is Vc square is equals to initial. When the body was there at a certain height and it is not falling, of course we have taken the initial velocity 0. So here the initial velocity is 0 plus 2 acceleration. Since the body is falling under gravity, the acceleration will be acceleration due to gravity. Now this is, you can say, displacement or the height covered by the body since it is coming down. So now from here to here, what is the height covered by the body? It is total of h. So it is h. Now what is Vc square? If you see, it is 2gh, isn't it? Now if this is your Vc square, can we now calculate the expression for kinetic energy? That is half mvc square. What is the value of Vc square? It is 2gh. So we are going to write 2gh. Okay. Now this 2 and this 2 is cancelled. So kinetic energy we are having simply is mgh. This is the expression for kinetic energy, and as we have seen here at point C, there is no potential energy. So what is the total energy at point C? Total energy would be kinetic energy plus potential energy. Kinetic energy is coming mgh, potential energy is 0. So again the total is coming mgh. Now if I summarize the things now, what do we have seen is that at point A, the total energy, that is the sum of kinetic energy plus potential energy, is coming mgh. Okay. At point B, again the total energy is coming mgh. Now at point C again, we see the total energy, that is kinetic energy plus potential energy, is coming mgh. So you see the body is coming from point A to point C, under free fall it is coming down. Although sometimes there is no kinetic energy and there is only potential energy, at some points there is some kinetic energy, some potential energy, and at point C, before striking the surface, there is only kinetic energy, no potential energy. So if you see, but in any case, when we are taking the total amount of energy, that is kinetic energy plus potential energy, every time the sum is coming mgh. That means whenever we are taking this k plus u, it is always coming mgh. That means it is not changing. So can we say that the sum is actually constant? That means it is not changing. And if it is not changing, the sum is constant, that means the energy throughout the motion, or if you are talking about free fall, the energy is conserved. One form of energy is converting into the other form, but the total energy is conserved. And that's how we say, or that's how we conclude, that energy cannot be destroyed. It can only, one form of energy can be converted into the other form. So this is an example of free fall. We can take one more example. As you have learned in class 9, you know about simple pendulum. I'm going to take a little time to explain this. Now if I'm talking about this a simple pendulum, here is the effective length and then we have bob, you know. Let's say that this is the point from where we are calculating. Now when the simple pendulum is at rest, okay, and it is ready to move, okay, it is ready to move, it is exactly the reference point. What is the height of the pendulum? No height. That means there will be no potential energy. Simply at this point, and you know that this point is known as the mean position. So at the mean position there is no potential energy, but then it is ready to move. It is ready to move on the either side of the mean position. So if it is coming to this side, it should have some kinetic energy with which it can move. So here there will be some kinetic energy. There will be some expression of kinetic energy. Let's say it is half mv square. Whatever velocity it is going to attain, that will be half mv square. Let's say the mass of the bob is m. Okay. Now it is moving, so it is coming to the one end. Let's say it is coming here. This is the position. Now you know that this is the extreme position. And you see, when it is coming to this side, you see it is actually attaining a height h. Okay, when it is attaining a height h, that means there is now some height, so it will have some potential energy, that will be mgh. And now when it is coming to the extreme position and it is not going further, that means the velocity of the bob here at this point is 0, because now it is not going any further, now it is going back. So here at this point the velocity is 0. If the velocity is 0, that means there will be no kinetic energy. So if you see now here at this point in the mean position, there is no potential energy but only kinetic energy. When it is coming to the extreme point, all the potential energy or all the kinetic energy is converting into potential energy. We are going to see the values are going to be same. So we are going to see that the kinetic energy is converting into potential energy and kinetic energy is becoming 0. That means whatever kinetic energy it has here, it is now moving, and meanwhile all the kinetic energy is converting into potential energy. Okay, and if you see it is going back again, then again one form will convert into the other form and it will go to the other side. So this is how the things work. You have kinetic energy, and when the body is moving, all the kinetic energy will be converting into potential energy, and then all the potential energy is converting into kinetic energy. One form is converting into the other form, but the sum is going to be constant, and that's how the nature works. There will be no wastage of energy. Only one form is converted into. Now we cannot destroy energy, and that's what the idea of conservation of energy. And there is some, I'm going to attach some topics, and I'm going to attach some pages so that you can read to yourself and you can see that how the things work. Okay.